Welcome everyone to Guided Study Group Week 6 of Statistics 100. This week we're gonna work on Lesson 6, and so let's get started. Lesson 6 is about the relationship between measurement variables. So some part of this material is kind of like overlapping on the previous lessons, but a lot of them also new. So in this lesson, we get into interact and know the concept of correlations. So correlations is just measure how close the values fall to a straight line, indicating the strength and the direction of the relationship. And so kind of like you use a scatter plot to maybe represent x and y and see like how they fall into a straight line with one another. And the range is from -1 to 1. So the closest to -1 and 1, the stronger the relationship, and the positive is going to be a positive rate, which means positive relationship. When one increase, the other also increase. And the direction, so that is the direction, positive or negative, and the strength is how close the values to -1 or 1. So the closest is to 0, then there will be less, the relationship is going to be weaker. We will conclude at r equals 0 that there's no linear relationship between the two variables, or the best straight line through the data is horizontal. Note that this correlation is independent of the original units of variables. So say if you change the unit of, say, like from meters to inches or meters to feet, there wouldn't be any changes in the correlations. It only depends on the standardized score of the variables. So it only depending on the data. So say R is because the correlation is calculated based on every values in the data and their standardized score. So it only depends on the variables in the data. Correlation is a descriptive result because it takes into account all of the values in the data, and it's just like one of the way to summarize the data. And it is sensitive to outliers, just like mean and standard deviation, because it uses up all the value in the data. So if there's outliers, the correlation is going to be drive towards it. So say we also have the concept of statistical significance. So if you find that a relationship is statistical significance, it means that there will be some relations between the variables that we're talking about, and that such relationship is not likely to occur by chance. It's important to, if we have a statistical significant relationship, it is important, especially in randomized experiment, to conclude like a causal relationship between the variables. But this is not possible in observational studies. You can only conclude about association, even with finding of significance. In reality, the causal relationship, there's no way to actually prove it. We can only design a better experiment with better control of the alternative explanation. So to make sure that the whatever measurements that we're doing, it's just gonna be on the variable that we're interested in, and we try to minimize the effects and also some possible contributions from any confounding variables or any interactions between the variables. We in this class, we're just gonna talk about linear relationship, and when we find the relationship, we're gonna check, kind of like look at the correlation and see if there's any outliers to actually make some conclusion about it. And note the fact that if you see outliers, it's not simple as just removing them and think that, okay, this doesn't making any sense because it doesn't match with the data. Sometimes those outliers will actually bring the insights into whatever you're trying to study. So the outliers should be kept, but with attention to it. So when you discuss it, you have to say that, okay, if there's any outliers or not, and on which direction does it affect the relationship. We're going to see that in one of the practice questions. So in this relationship, we need to check for these are the possible causes that might affect the results that we have. Whether we choose a response and explanatory variable correctly. So make sure that whichever caused the other or like actually brings the effect is the explanatory, and the one that get the effects is the response variable. Or whether the change is in the explanatory variable contribute along with other variables to change the response. So kind of like any interactions between the explanatory variables and something else that can affect the response. Any confounding variables or whether both variables may have changed together over time. So would time and space have any effect on the change of the response variable, or is it just the effect from the explanatory variables? And then lastly, whether the association between the variables might be just a matter of coincidence. So sometimes we just like try to measure something, but it happens to be, say, like a specific occasion. So say, on like a holiday, then we have like more people staying at home, but we're trying to draw like a relationship of like how their work, like how intense their work is with the data they take. And we just happen to take the survey maybe say like on a national holiday week, then that would just a coincidence. We also have the important concept of regression. So regression is kind of the one is gonna actually allow us to make the predictions on the two variables. So what regression do is essentially find the best straight line to fit the data points on the scatter plot, and we end up having the regression equation, which we can use to predict the response variable using the from what like a certain value of explanatory variable. The regression analysis includes that explanatory variables on the x horizontal axis and response outcome variable on the y vertical axis. We also have the basic equation BA plus BX, with A be the y-intercept, so the y value when x is equal to 0, and B be the slope of the line. So the slope of the line is defined as the change of y over the change of x. So if x increase by maybe 1 unit, how much does y increase? We also have the most kind of like one of the most common method to find the best straight line to fit the data points, which is called the least square lines. So find the line closest to all the data points using try to minimize the standard errors from try to minimize the residuals R square. But we wouldn't get too much into that calculation unless you guys proceed to stat 200 or like higher level of class, like statistic 400 something. We also need to know how to interpret the y-intercept and the slope. So the y-intercept is, as we say, defined as the y value when x is equal to 0. However, it might have some physical meaning or not, depending on if x equals 0 is in your data set. So say if we're talking about the score, right? Or we're talking about like maybe the temperatures is, no, not temperatures, that's such a bad idea. If we just talk about something really negative, no, always positive, so say like the number of oranges that grows on the orange trees, usually 0 is not in the data point. So no, in the data, so it's not in the data set. So that at that point the y-intercept would not have any physical meaning. But if it is, then we can make an interpretation of that. The slope, as we said, is just the change of x per change of y. No, change of y per change of x. So what is the change of y when x increased by 1 unit? And the warning of extrapolation. So this is not just in statistics, but any form of science that use statistic or linear regression as the kind of like the model to build their relationship. Extrapolation might always be a problem. So say it might feel like when we talk about an isotope, so like how the absorption, so say at first the absorption is really fast and then it go level down, which is when it reaches saturation. So say extrapolation. So the linear model is only correct here. So if you go beyond this point, then the linear model would not be more correct. So say if you only make the regression based on the data points in this range, but you try to predict a value here, then extrapolation is then the prediction is no longer accurate because it's based on a non-linear model now and not a linear model. So now we have some practice questions. Again, as always, if you guys join me online, please feel free to mute me or stop me at any time if you want to work on this thing alone, or because I'm just gonna go ahead and give the answer. So we have a first question. Suppose a correlation of negative 0.65 is obtained from two measurement variables. Which of the following might represent the slope that would be found if a regression equations were calculated? So we have a correlation of negative 0.65. So it's kind of like a relatively strong relationship, and the direction is negatively kind of like indirectly related to one another. So with one increase, the other will decrease. So when we come to the regression a plus bx, so as x increase by 1 unit, y will decrease. So you have b will be the change of y over the change of x. So when x increase, which is positive, y is going to decrease, which is negative. So negative over positive is just going to be a negative. So the regression equations will have a negative slope. And so among these answers, A is the most possible one. And so after this exercise, one thing to kind of like make a note to yourself is that the correlation value is usually going to have the same side with the regression equation slope. So the correlation here, R, is usually going to have the same side, either both positive or both negative would be the slope of the regression equation. Then we have a second questions. Again, stop me if you want to work on it. The correlation between the height and weight of the people in a small room was 0.6 until basketball players LeBron James, with 2.03 meters height, entered the room. At that point, the correlation will be what? So at first you have a correlation with 0.6 between height and weight. But then LeBron James, who have a real maybe a regular weight, but a very a much higher height compared to the rest of the group. So say first of all is somewhere here. So the maybe all of the points are in here. Then you have suddenly a point of LeBron James which is like this high. So it's gonna draw the entire regression. The relation goes up because he has much higher height compared to weight. So our answer is going to be correlation. He has much higher height. It's going to be much higher than 0.6. So it's going to be, this is height and this is weight. The correlation will now be really strong because they have a factor. We have one of the data points that is very has regular weight but really much higher height compared to the other. Now, yeah, that's pretty clears up. Then we have question 3. For which of these pair variables could one find a correlations? So a correlations is just like a beginning, we say the name of the lesson is relationships between two measurement variables. So the two variables have to be quantitative and measurable, so in a number form. So we cannot find a correlation between categorical variable. So any answer that have categorical variable is going to be eliminated. That's why 8 is correct, because we have height and weight. Gender, I believe at first sight, both of them are called categorical variables, so they cannot be used. Age and IQ, both of them are numerical variables. Hours study for an exam and numerical score on an exam. Surely that works. Gender and favorite color of car. Again, this one would not work because both of them are categorical variables. So we have A, C, and D. So the answer is going to be F. If you have any questions, again, as I always say, email me at any time or email your instructor. I'll be able to answer it. I always try to put my email back at psu.edu. Then I will try my best to help you guys out. Then we have question 4. Again, stop it if you work on it. If you want to work on it alone. Which of the following, if left to stand alone, is the weakest evidence of a possible causal connections? So let's read what we say. A, many potential confounding variables have been ruled out. So it's a good evidence that there's a causal connection effects because we make sure that any alternative explanations has been excluded. So this one is a strong variable. The connections were shown to hold under varying conditions. Which is again also a strong evidence because now the connections will hold in many circumstances, and so there must be a relationship between two variables because now other variables that can affect it, even though they changes, the relationship is still there. So it means that there must be something related to the explanatory variables that will relate to the response variable, and it's not depending on other confounding variables because those change, but this thing doesn't change. That is correct. It is a strong evidence. The data appear to have a moderate association on the scatter plot. Well, I mean, the moderate association, that might make sense, so I keep it there. Now let's read D. There's a solid scientific explanation for a cause and effect relationship. So if this is definitely a strong evidence, so the answer is C. And so the way that I'm gonna make sense of it is that you need a strong association on the scatter plot at least to say that there's a causal connection. Especially in the case of observational study, a causal connection cannot even be concluded. So if you want to conclude it, there's a causal connection, at least you should have the conditions that is a strong association on a scatter plot. And just look at the way that they make it, association. So usually when you have association, there's no way that you can use it as a causal connection because it means that the study here is observational and not randomized experiment. So next one is question 5. Stop me if you want to work on it. Suppose the correlation is found to be very weak. What statements given below are correct about the relationship between the two variables? 1, there's no linear relationship between the two variables being measured. That might be right. There may be a different type of relationship between the variables, just not a linear one. That might also be correct. Yeah, if you find the correlations and it's using a linear model, then usually it's very weak. There may be separate linear relationships that are being masked by a third variable that was not accounted for. That makes sense as well. So these are all the possible explanations about why the correlation is very weak. And so the answer here is 3. All of these can happen. And look at the way that they phrase it. It's like there may be. So since it's maybe, if there's a chance that they're correct, then we're just gonna choose that they're correct. Now question 6, again, stop me if you want to work on it. The data below plot students' ideal weight in pounds against actual weight in pounds with the correlation be Pearson correlation be 0.91 and p-value is 0. If the units measure for the two variables found in the problem were changed from pounds to kilogram, what would be the value of the correlation when knowing what 1 pound is approximately 0.45 kilograms? Now this is coming back from the to the first slide that I mentioned, correlation is not dependent on the original units of variables. So it's gonna stay the same as long as the correlation is just the strength of a relationship. It is not like a a regression equation. So it doesn't have anything to do with the units. It's just showing how strongly one is affecting another. So the unit doesn't affect the strength of the relationship. Therefore, the correlation is the same, which is 0.91. Now we have the last questions. Again, mute me if you want to work on it alone. A negative correlation has been found between time spent watching TV and exam score. Which of the following is not true? So a negative correlation between time spent watching TV and exam score. So which means when one increases, the other one seems to decrease, which is not true. One may conclude that an increase in the time spent watching TV caused the exam score to decrease. I mean, there's a correlation, but you don't know about observational studies or is it randomized experiments. So that might be true or that might not. But it's more likely that it's not true because you're lacking the specification of is a randomized experiment or is it a observational study. This says that the time spent watching TV is an explanatory variable and the exam score is a response variable. Again, this is not really like the case. Because they didn't specify what they actually measures, and the explanatory variable or response variable is only applicable for an randomized experiment. So it's not like observational studies in those cases. And usually, yeah, so this doesn't specify what do they actually measure. They just say we found that correlations. So they can measure a bunch of other things and can end up with this result. See, a possible value for the correlation is 0.32. Now we're talking about a negative correlation, so the correlation value has to be negative. So this one is definitely not true, and there's a high chance that these are not true because they didn't specify if it's an experiment or not, and even if there is, they didn't say if there's evidence of a causal relationship, right? Therefore, we're going to choose all of the choices are not correct. And this one I found is a very quite challenging and confusing one. So like at the same time, you can determine if it's right or wrong, but then you have to look at the context and the way that they phrase the answer. So if you have any questions with this one, please feel free to email me or Dr. Ellie to work on this. We're gonna try to explain better to you. So the final note, all the weekly review sessions available on my YouTube channel with that link. The next review is next Thursday, 10 p.m. Eastern Time. And please try out the practice problems after this review. I feel like that's really helpful before you guys attempt the quizzes this week because I found this week is a little bit confusing and challenging at the same time. So it's a good opportunity to practice. If not, I'll see you guys next week and have a great weekend, guys.